Depth estimation is a very important problem in computer vision. It is very extensively studied and it is one of those problems that has enormous value. Being able to estimate depth of a scene is important for robotics, for AR, VR applications, for autonomous navigation, for 3D modeling, for 3D reconstruction, and the list goes on and on. Recently, this month, October 2024, Apple released a paper named Depth Pro. This paper is titled Depth Pro Sharp Monocular Metric Depth in Less Than a Second. Now, the keyword here is monocular depth. In this video, we are going to talk about this paper and we will see how we can set this code up and run this method. I'm going to demonstrate the applicability of this method on a test scenario that I created. So stay tuned until the end. Welcome back to the channel, guys. My name is Dhruv. I am an engineer at Convolve. At Convolve, we help small, medium, large enterprises with their problems that can be solved using computer vision and AI. We have expertise in helping you implement computer vision solutions in your workplace, in your production environments, and we've had experience with helping improve safety, compliance, helping you build better and more safer and efficient workplaces. Now, guys, talking about this new method, this new paper, Depth Pro Monocular Depth Metric Estimation. First of all, what is monocular depth estimation and why is it important? Monocular depth estimation is estimating the depth of a scene using one single camera. That is a mono camera. Monocular means one. One single camera being used to estimate the depth. That's what monocular depth estimation is. Now, why is this such an exciting and interesting field of study? The reason is that the depth estimation problem in itself requires two cameras, a stereo camera or a depth sensor, to be able to give good results. With a single camera, getting the correct metric depth is very hard because a single camera is not able to triangulate the depth and it does not have the information about the scale of the scene. However, with the advent of deep learning models, now with cameras, we are able to in a better way estimate the depth with reasonably correct scale, and hence that's where this monocular depth estimation, the study of monocular depth, comes into the picture. Now, for the sake of motivation, what is a use case? The most evident use case is autonomous driving. If you have seen a Tesla or if you have driven in a Tesla, you would know that Tesla uses only cameras for all the autonomous driving. That is camera sensors for everything, right? So if within that particular vehicle, the depth estimation is required for their autonomous driving stack to function properly, and being able to estimate depth from a single camera comes into picture, right? So as the Tesla drives by, it's able to understand the entire world, the distance to objects, the depth of different objects, and it's able to navigate through the scene. That's one great application of depth estimation. Similarly, in robotics, in other robotic applications, autonomous warehouse robots, if they have cameras, they are able to determine the depth of different objects, different obstacles, and that can help them navigate around those obstacles. Being able to estimate depth from cameras alone, like Tesla does, is important because it helps you get rid of other bulky and expensive sensors such as LiDARs, and hence this is such an exciting field to study. Now, guys, let's go into the details of this paper and the code. So here on the screen, you can see this paper that came out in October of 2024. So it's very recent. Depth Pro Sharp Monocular Metric Depth in Less Than a Second. So guys, this is the abstract of the paper, and here you can see some sample output images. If we go to the paper, we can see the entire manuscript, and this is a very interesting paper with amazing authors. All of these are veterans in computer vision, and they have open sourced the code. So guys, just as a motivation, here are some of the results that they've showcased, And you can see that this is the input image, and these are the comparison of different models, different state of the art models against Depth Pro that Apple has released. And here you can see how well it's able to estimate the depth for these whiskers of these cats. This is extremely hard, right? Being able to correctly determine the depth in with such accuracy and precision. That's what they are showcasing. If you are interested to go into the details, you can go over the paper. In this video, we won't go into the details or the technical details of the paper, but we would focus on the code and sample implementation on an experimental setting just to showcase the effectiveness of this method. So here, this is the GitHub repository. That's where the entire code base is. And Apple has been generous enough to open source the code. Not something they do very often, but in this case, they have done it. And here we can see that we have been given the instructions on how to set this repository up. Now, guys, the first thing I want to point out is that this method gives you the metric depth in meters, and it's able to essentially give you an absolute depth value for different objects in the scene. So it's able to give you a depth map for that particular scene. So these are the instructions on how we can set up the environment. So essentially, you have to create a virtual environment, and that's the right way to do it, or the best way to do it. Instead, otherwise you will end up screwing over all the other dependencies that you have and have a lot of issues. So this is the command to create a new virtual environment Depth Pro using Python 3.9. So we ran this particular command. Over here, we have already created the virtual environment. You can see the Depth Pro has been activated in our command line. So we won't be running this again, but this is pretty straightforward process, right? And the next thing is to install, run the install script to install all the required dependencies in this particular package that comes with the source code. Once you're done with that, you can download the pre-trained models. So the authors have made the pre-trained checkpoints available, and running that script will basically, this is the GitHub repository that we have cloned on our system. This will basically download this Depth Pro model on your drive. It will download it on your hard drive, and here you can see this particular model. It is around 1.7 gigabytes in size, so it's a very big model with a lot of parameters. And this pre-trained model can be used for you to then do all your depth predictions there on. This command over here can be run on the example image. We won't be running this command, but I'll be showing you a sample code to run this particular this particular method on your specific data. So guys, let me show you over here. Here on the screen, you can see a test script that was created. So we import the image library from PIL, and we import Depth Pro, that is this method. In this line over here, what we're doing is we are essentially creating a model and the transform. And that model is being initialized with in the evaluation mode for you to be able to evaluate the output. Then we are essentially loading an RGB image. So let me show you the image that I took for the sample demonstration purpose. Here is the data, and here is that particular image. So essentially what I did was I put a measuring tape on the ground, and I put two different objects across that measuring tape. So I know the ground truth. I know the distance of those objects from my camera. And my experiment is to run depth estimation on this particular scene and get the distance to this bottle and distance to this box and see how accurate that depth estimate is from this Depth Pro model. So here's where that particular path to that image has been provided, and we have essentially taken that image, transformed it. This is the internal transform method that basically takes an input image and transforms it into an input that the model expects. And the next step is just to run inference on the model. using that particular image that we've just loaded. And then all the output from the model is stored in this prediction object, which has the depth as a part of it. It's like a dictionary output. So this model method, infer method, outputs a dictionary, and that dictionary has the prediction for depth and the focal length of the camera. And then over here, this code essentially is just plotting the predicted depth onto a depth map. What we're doing is we are essentially first transferring the depth to the CPU and transferring it from a tensor to a numpy array. And then we are normalizing that particular depth map. What does normalization do? Well, matplotlib, when it's outputting or displaying an image, it is expecting normalized coordinates or normalized values from 0 to 1 or 0 to 255. But since the depth can be any value between um, 0 to infinity, and it could be floating point numbers, we want to normalize it to bring it between 0 and 1 so that matplotlib can understand. And the way we do it is we take the depth, we subtract the minimum depth in that depth map, so the minimum depth in the scene that was predicted by the model, and we divide that with the range of depth. So the max depth minus the min depth, we do that computation here and divide, and this will basically normalize the depth map. And then we essentially output the display the depth map. So let's run this code and see what kind of output we get. So this python test.py is going to run this code. So I'm gonna just execute it. Apple or the paper claims that they do this within a second. It does take a little longer than that, but it's also because there is loading of the checkpoint weights, which is around 1.7 gigabytes that's being loaded onto the memory. Once it's loaded, I believe then the inference is pretty quick. But I haven't done full-on evaluation with regards to the inference speed. Again, it also depends on the hardware that's being used. So while it runs, let's just wait a bit for this to complete the evaluation. So here it is. We've seen the depth map, right? So guys, see how smooth the depth map is. And over here we have the color bar with this color yellow being the furthest objects and dark purple being the closest objects. And here we see the depth to this bottle and this box. So almost the depth to the bottle is around 1.0.135. So guys, if you see on the screen at the bottom right of this particular figure, uh, the XY, the pixel location, and the corresponding value can be seen. So here, for example, right now the value is 0.138 where my cursor is. And for this box, currently the value is 0.36 where my cursor is. Now, these are normalized depth values, right? In order to get the metric depth or the depth in inches, we have to do some unnormalization of this particular data. So we have written a code, a program to do that unnormalization. And the way it's done is essentially you need to know the minimum depth that was computed, which is 0.326131108. We have put it here. And we need to know the max depth, which is 3.417503. Using this minimum and maximum depth and the predicted value, which comes from the depth map, that's the normalized value. We multiply that by max depth minus min depth, and we add the min depth in it. That will essentially unnormalize the value and give us the answer in meters. From normalized, we have gone to unnormalized value. And over here, multiplying this with 39.37 converts meters into inches. The reason this meter into inches conversion is being done is because the measurement on the measuring tape is in inches. So just to make it a lot easier for us to understand and compare, we have done this particular conversion. And the value from the for the distance of the bottle is 0.135 on average, as we've seen from this particular figure. Let's just take 0.135 as the average and run this particular code. So here is that particular code, unnormalized.py. It gives around 27 inches as the output. Now let's do it, run the same thing on the box, and the box over here is, let's say it's around 0.35 in terms of the value, 355, and when we run it we get 54 inches, almost 54.4 inches as the output. And now the next step is to see if this is the correct output or not. So let's compare it by pulling up that image. So guys, here on the screen you can see an image of that setup taken from the top view, and here you can see the actual metric distance of these particular objects. So this is around 24 inches, and this particular box is starting at around 48 inches. Let me show a better image here. So this is for this particular bottle. You can see 24 inches over here, or it starts around 23 inches or so, right? And then this is the box, which starts around at 48 inches roughly. Now, if we go back to our code here, the output for the bottle was around 27 inches and the box was 54 inches. Now, this is the output from the depth estimation model. Again, it's not entirely accurate, but it's close. So the demonstration here is that it is giving absolute metric depth. It's not something that is up to scale. Oftentimes, monocular depth will give you results that are to scale, which means that uh, instead of predicting 24 or 48 for these objects, the algorithm or the depth estimator will predict 4 and 8. Again, scale or ratio wise, they are same in terms of one is uh, say 1 unit away and the other is 2 units away. So the ratio between the distance between the two is 1:2. However, scale wise, it is lacking the information about scale because, as I said before, and as if you have worked with monocular depth estimation, single camera depth estimation is usually up to the scale. But here it is very close to the actual, so it does not seem that it requires any further scaling to get the correct answer. So this was the ML Depth Pro setup and implementation and a test using that particular method. This method is extremely new. The results shown in the paper are extremely promising, and it's amazing what we can achieve using this particular method. I hope through this video you were able to understand how you can set up and you can execute this method. And then further in downstream tasks, as we've talked before, there are so many different applications in robotics, in AR, VR, and Apple's work on the Vision Pro is something that is leading to a lot of advancements in the computer vision industry because it's all based on virtual reality and being able to have good depth estimates, good 3D reconstruction of the environment is something that is paramount. Again, for robotics, it has ample amount of applications. That's it for this video, guys. If you like this video, please hit the like button, subscribe to the channel, and hit that bell icon so that you are notified about any new video that we upload. Thanks again for watching, and we will continue to put more and more videos on computer vision, robotics, 3D reconstruction. So stay tuned to our channel. Thanks again for tuning in. I'll see you in the next video.